My project is on collagen alpha-1 chain isoform 2 preproprotein and its relation to Ehlers-Danlos syndrome types 1 and 2. First up, we have the structure of my protein. So the gene is collagen 5 alpha-1, which codes for pro-alpha-1 protein. This top line is the primary structure, which is composed of the amino acid sequence. This was determined by copy and pasting an unknown nucleotide sequence into the BLAST function on the NCBI website. This gave me the gene and the protein, and showed that my protein was 1,838 amino acids long. So this is just a little segment from amino acid 1611 to amino acid 1680, with the asterisks denoting every 10 amino acids. In yellow is one of the common nonsense mutations, and in blue are the calcium binding sites. The next two lines are the secondary structure predictions taken from two different websites. The first website being the Chow and Gasman Secondary Structure Prediction Server, and this website being GOR4 Secondary Structure Prediction Method. In both of them, the E stands for beta sheets, H stands for helix, T stands for turn, and C stands for coil. Highlighted in red are where the two secondary structure predictions match up, and highlighted in green are where the two secondary structure predictions match up with the tertiary structure prediction as well, which is seen here. This was determined by copy and pasting the amino acid sequence into the website DTU Bioinformatics Department of Biology and Health Informatics CPH Models 3.2 server, and then taking that and putting it into the PyMol function on my computer. This showed me that the tertiary structure is amino acid 1610 to 1836, which is known as the fibrillar collagen C-terminal propeptide domain. In PyMol, I was able to color code for secondary structure. So in blue, we have helix Cs, pink are the turns and coils, and red are the beta sheets. And in green is where the two secondary structures match up with the tertiary structure. So this section right here, for example, is this section right up here. In yellow, I'm just showing where the tyrosine 1654 mutation is. And here in blue is just showing where the calcium binding sites are. So we have glutamine 1660, asparagine 1659, aspartic acid 1657 and 1665, and cysteine 1662. Down here is just another structure for pro-alpha-1, just in a different way. On this side is the N-terminal, which is composed of non-collagenous 3 region, signal peptide, TSPN1, which is the proline-arginine-rich region, the variable region, collagenous 2 region, non-collagenous 2 region. Right here is the main triple helix collagenous domain, and down here is the C-terminal propeptide. So collagen 5 alpha-1 codes for pro-alpha-1 chain of type 5 collagen. Type 5 collagen is found in tissues and is an important part of maintaining structural support of the epidermis, as well as regulating the assembly of heterotypic fibers composed of both type 1 and type 5 collagen. This first picture shows the molecular function and the biological function of pro-alpha-1. So pro-alpha-1 aids in the structural support of different tissues in the cell by binding laminin, which is important to extracellular structure and support. Biologically, it is involved in collagen fibril formation, and it is specifically needed to initiate fibril organization and synthesis, shown here. This picture shows the normal situation in which collagen 5 alpha-1 in the form of pro-alpha-1 creates these areas of fibrils that are actually relatively consistent in their diameters. So this happens by collagen 5 and collagen 1 copolymerizing into heterotypic fibrils through a regulated fibril assembly process. Primary fibrils nucleated in the presence of collagen 5 form short fibril intermediates that are then grown by linear and lateral fusions. to create a heterotypic fibril, which then leads to a population of fibrils with relatively consistent diameters, as you can see here. So studies have revealed that collagen 5 in the form of alpha-1, 5, appears morphologically as thin filaments that are 5 to 10 nanometers in diameter. And they serve as a structural component in the basement membranes of the epidermis, thereby contributing to the stabilization of the epidermal-dermal interface, which you can see in this photo. You can see that the epidermis and the dermis are both composed of collagen, and collagen soothes the skin, promotes moisture, and it promotes regeneration and restoring of the skin. Now, this picture may look familiar because it is. It is the C-terminal propeptide, also known as the tertiary structure, and it's highlighting the calcium binding sites. And I bring this back because the C-terminal propeptide also plays a crucial role in tissue growth and repair by controlling both the intracellular assembly of procollagen molecules and the extracellular assembly of collagen fibrils. And it binds calcium ions in these sites, which is essential for its function in maintaining the structure of the epidermal-dermal interface. This slide shows some common locations of mutations, and specifically the more common ones are nonsense mutations, causing type 5 collagen haploinsufficiency, which I'll talk about in the next slide. But I just wanted to show that this mutation that I noted previously, tyrosine 1654, is right here. And this is just another photo to show that premature stop codons at different amino acids is a major cause of type 5 collagen haploinsufficiency. So as I just said, the most common mutation in pro-alpha-1, 5 protein is a nonsense mutation. So these mutations generate an unstable transcript that is rapidly degraded by NMD and result in an overall reduction in collagen 5 levels, which is also known as haploinsufficiency. Haploinsufficiency is when one working copy is not sufficient for normal expression of the gene's function. So up here you can see there are 2 doses of the product leading to a wild type, which is good, but down here this is haploinsufficiency, where 1 dose isn't adequate enough, so it leads to a mutant. This photo shows how collagen 5 haploinsufficiency, which is right here in the middle denoted by a plus minus, leads to fewer fibrils being nucleated and form into either normal or thick irregular fibrils. So compared to this normal fibril, which are all kind of the same in diameter, over here you have some that are big, some are irregular, and they're just kind of weird looking. Reduction in the amount of type 5 collagen is central to the pathogenesis of classical Ehlers-Danlos syndrome. Now, Ehlers-Danlos syndrome is an autosomal dominant connective tissue disorder characterized by skin hyperextensibility, scarring, joint hypermobility, stretchy skin, and easy bruising. The most common molecular defects result in nonsense-mediated decay of the mutated collagen 5 alpha-1 mRNA, which means in a haploinsufficient person, which is in red here, they are going to have less collagen 5 alpha-1 than the wild type, which is going to lead to Ehlers-Danlos syndrome. And why this happens is because a reduction in collagen 5 leads to inadequate maintenance of biomechanical integrity of collagenous matrix. A defect in collagen can weaken connective tissues in the skin, bones, and blood vessels, which can lead to classic Ehlers-Danlos syndrome. If collagen is weaker than it should be, tissues in the body will be fragile. This can make ligaments and joints particularly loose and stretchy, leading to the classic hypermobility associated with classic Ehlers-Danlos syndrome. Collagen fibers protect the integrity of the skin and blood vessels, so if something weakens the collagen, such as not having enough collagen 5 alpha-1, then you might be more susceptible to bruising or scarring. And this picture just kind of summarizes what I just said. Collagen 5 alpha-1 gene haploinsufficiency, you have initiation and lateral growth are impaired, so you get a reduced number of collagen fibrils and more larger irregular fibrils like here, leading to classic Ehlers-Danlos syndrome. Classic Ehlers-Danlos syndrome is characterized by hypermobility of joints, stretchy skin that is soft and fragile, unusual scarring, and easy excessive bruising. And this leads to a lot of complications such as increased pain, poor wound healing, dislocations, fatigue, and delayed motor development. Now I'm going to play a video of a patient with Ehlers-Danlos.
Hi, I'm Hallie Pollard. I'm 12 years old and I'm a patient in the pain management clinic.
I'm Katie Bentley and I'm Hallie's mom. Hallie was doing ballet at the Cincinnati Ballet, dancing in the Nutcracker, Cinderella, things like that.
People in my dance class, they would say, "Oh wow, you're so flexible. It's awesome. You can do this and that and this and that." But it hurt my body afterwards.
We started noticing that she seemed like she was just having little injuries a lot. And then all of a sudden, we noticed that she started having a lot of pain in a lot of places. I mean, if you didn't know Hallie, you would think that maybe she was just imagining it because there was so many pain spots on her body. I mean, her chest hurt, her legs hurt, and her head hurt. I mean, everything hurt. And Hallie's not a complainer. She's not one to just sit and say, this hurts, this hurts, this hurts. And then when you would give her something for it and it wouldn't go away, we knew something was wrong. It was real frustrating because as a parent, where do you take the kid that has pain everywhere?
I'm Dr. Ken Goldschneider. I'm the director of the Pain Management Center, and we're here in clinic. We generally start with how she's been doing. And what we've been doing just now is talking about her interest in theater and dance, because people with hypermobility syndromes can do very well at dance, but it can become expensive to their joints. And what she's learned really well is to balance how much she does that she enjoys without going too far and straining her joints, therefore causing more pain. We're familiar with Ehlers-Danlos syndrome and with joint hypermobility, which we hear over and over again that people just don't know what it is. And even if they know what it is, they don't know what that means. Overall goal number one is function. These kids have to have lives. And when I say get a life, I mean it in the most positive, wonderful way. Because a lot of time pain gets in the way. I mean, it hurts in the first place. It's a message that originally means stop, protect me, don't do anything until I'm safe. But the problem is getting past that point where you say, you know what, I know I'm safe and I can work through the pain until it heals up and I can modify my lifestyle and be better and not have pain. That's a big process to go through. But once gone through that process, through this holistic process, then having a life is the goal. The best thing we did was get into that pain clinic and do physical therapy. We just learned so much. It was a huge education on our part.
I started out by being in bed, and then with the help of pain clinic and physical therapy and headache clinic and all the other doctors I've been seeing, I've gotten to have my life back. And pain is not controlling it anymore. I'm controlling it.
So this is just showing you where to go if you want to go to the Ehlers-Danlos Society. And their mantra is, when you hear hoofbeats behind you, you don't expect to see a zebra, but sometimes when you hear hoofbeats, it really is a zebra. So the link to their website is right here at the top, and on this website you can find everything from volunteering to donating to starting a fundraiser to, if you actually have Ehlers-Danlos syndrome or know somebody that does, this is a great website for them to go to for clinics, for finding hotlines, for finding people that also have the syndrome, and just making more and more people aware of what Ehlers-Danlos syndrome actually is. And the entire month of May is EDS, Ehlers-Danlos Syndrome Awareness Month. So if on social media you see hashtag #MyEDSChallenge, then you'll know that that means my Ehlers-Danlos Syndrome Challenge. And that is that. That's the end.